we will discuss package formation. So, sliver has been made. The next job to be done is to form a package. The sliver, as we know, is very weak, and therefore, what kind of package we should have, so that the sliver may remain protected and it should not get damaged during handling. It should not get entangled or stretched when we want to remove the sliver from the package. So, these are the requirements of the packaging mechanism that we should follow, and to fulfill this requirement, the sliver is deposited in a cycloidal fashion, that is in the form of spirals or coils in a container which we call can. It is basically a hollow cylinder. The cycloidal deposition is shown in the diagram. We see that the outer circle indicates the inner part of a can, and the smaller circles are indicating the coils being formed by the sliver. So, if we have a deposition like this, then the withdrawal of the sliver becomes easy and it does not disturb the rest of the material or does not get stretched too much. So, this kind of mechanism or this kind of coiling is followed. Now, we will discuss what kind of motion is required to create such kind of coiling of the sliver. It needs two simultaneously occurring rotary motions. You can see in the diagram that there are two types of coiling being shown here. One we known as under center coiling on the left hand side of the diagram, and the other one is over center coiling. Now, what is the difference between these two coiling? In the one case, the diameter of the coil is less than the radius of the outer circle, shown by the very dark form line. In the other case, if you see carefully, the diameter of the coil is greater than the radius of the outer circle. So, this is the basic difference between these two. Both type of coiling are practiced, and we will study them in details in the subsequent slides. So, one for laying the sliver in the form of coils, and the other motion is for the continuous shift of the coil center during laying, so that successive coils do not fall on each other. So, if we want to have such kind of arrangement, two simultaneously occurring rotary motions are required. It is also important to ensure that the gaps between the successive coils are not too far from each other, nor the coils should overlap each other. So, because each coil has a certain width when it falls, and we have to see when we make one coil, then as we go to the next coil should not fall on the top of the very first coil, it should move a bit. So, what we do is that as we keep generating the coils, the center part of the coil keeps on moving also along another circle, and that is how two types of rotary motions are required to produce such kind of cycloidal deposition of sliver. Now, cycloidal deposition results in the formation of a hollow space. If you see in the diagram, there is a hollow space. So, the hollow space is here, this is the hollow space, here also there is a hollow space. This hollow space will get formed here and here. This space avoids overlapping of sliver layers at the middle of the can and the creation of a central pyramid shaped column of material, leaving the site partially empty. This is the purpose for the creation of the hollow space. If you do not create that, then the problem will be that creation of a central pyramid shaped column which will be formed, and the stack of material, the stack of this sliver in the form of coils will take a conical shape. So, we want to avoid that, we have to have a hollow space. Ideally, the hollow space should be 1/4 to 1/3 of the circle formed by the outer profile of the sliver coil, as shown in this diagram, that is DC. Some gap should be left between the coils and the inner wall of the container, that is the can, so that the sliver can be withdrawn without undue stretch or friction. So, this circle that is shown here by this firm dark line, this is showing the outer profile of the coils being led, and this should be slightly smaller than the diameter of the can, so that little space is left and there is no friction between the sliver and the inner wall of the can. So, to avoid that, we want to maintain little gap. Now, we will discuss about the type of coiling. As told to you that there are two types, over center coiling and under center coiling. Now, in the over center coiling, on the right hand side, the coil diameter is larger than the radius of the can. So, as I told you earlier, that is much larger than the radius of the can or the radius of the bigger circle that we see here. The diameter relation is diameter of the can and diameter of the coil should have a value around 1.45. This is what we maintain. Large coils are better with small to medium size can diameter, since lower speed of the coil laying mechanism can be used for same circumferential speed, leading to reduction in force, noise and wear. This is the purpose why you go for larger coils are better with small to medium size can diameters. The package capacity also increased by 5 to 10% when you go for over center coiling, that is this type of coiling. From here, if we go to the next one, under center coiling, the diameter of the coils is smaller than the radius of the can. So, here this is the diameter of the coil. So, coil diameter is from here to there, and the diameter of the can, if we say, then it is from this point to this point. This is the radius of the, not diameter, radius of the can. So, the relationship between these two is dC by dl is 2.5. This is suitable for large size cans. The smaller is the size of coils, the smaller will be the size of the coil laying mechanism, and hence less mass is to be rotated. Therefore, for larger cans, and today most of the machines, modern machines are having very large can diameter, so that we can pack more sliver into a can. So, in these big cans, the coil size is much less than the radius of those cans. We will discuss now the dry part of the can. A little interesting point here to which we will see now. Now, this is a very simple diagram of the can diving mechanism which is shown. The vertical blue lines are indicating the can, which is basically a hollow cylinder, is resting on a turntable at the bottom, and at the top we have a coiler plate, and then we have coiler calendar rollers. This side we have calendar rollers, and the drive is shown also in the diagram. The can is offset by an amount s from the center of rotation of the coiler plate. So, if we see here that the diameter of the plate and the the center line, if we compare, then we will see there is distance of small s between these two. So, and that distance is shown here. The can is offset by an amount s from the center of the rotation of the coiler plate. Generally, the can moves in the direction opposite to that of the coiler tube. As the sliver is laid, it receives some nominal twist. However, the amount of this twist being too low, it has no practical value. Besides, this twist is nullified when the sliver is withdrawn from the can. So, in the sliver laying mechanism, theoretically we are also inserting little bit of twist, but practically this twist may be considered to be nil, and even if we consider twist is there, this twist will vanish when we remove the coil from the can. If we look at the drive part in details, then we will see that the drive must ensure the rate of coil laying must be equal to rate of sliver delivery by the colloidal calendar rollers. These two must match. While coiling, whatever length of sliver is required, the same amount of length of sliver must be delivered by the coiler calendar roller. If they do not match, and if we are underfeeding or overfeeding, then we will have problem. Underfeeding would result in sliver stretching, that is, the laying mechanism demands more sliver, but we feed less, and then hence there will be stretch on the sliver. On the contrary, while laying, the length required, if it is less than what I am feeding by the calendar rollers, that is, I am overfeeding, then the coiler tube might get choked. This could be another possibility. So, this should actually perfectly match as stated in the in the slide. The rate of coiling must be equal to rate of delivery. Now, what is the rate of coiling? For one revolution of the coiler tube, the length of sliver laid is going to be pi dl. The length of sliver delivered per coiler tube rotation. From here, if I go through this set of gears and try to find out how much length of sliver is delivered per coiler tube rotation, then we will see that it will be 1 into P by O into Q by R into pi d, where P, O, Q and R are the teeth of the gears shown in this diagram. Small d is the diameter of the coiler calendar roller, that is, it is this roller which is coiler calendar roller. So, theoretically, as per this stated condition, we can say pi dl must be equal to this, and from here therefore, we can write that small dl by d is going to be equal to this. So, there is definite ratio between the diameter of the coil, diameter of the coiler calendar roller. This ratio must be equal to the gear ratio featured here, that is P by O into Q by R. So, the way these gears are chosen, P, Q, R and O, that is this ratio P by O into Q by R must be equal to small dl by d. Otherwise, we will have a situation of either underfeeding or overfeeding, and therefore, either stretching of sliver or possibilities of choking of the coiler tube, because the sliver is made to pass through this tube. They are pushed through this tube, and because the tube is continuously rotating, hence the coils are getting formed and they are being laid inside the can. We will come now to the other important small part of the machine called trumpet. The trumpet consists of two parts, a plastic trumpet piece and a metal insert. In some machines it could be both could be made of metal sheets. The trumpet must ensure smooth passage of the sliver through it without any hindrance, so as to avoid its clogging or choking. So, we have to be very careful about that this trumpet has to be very clean, polished and smooth. So, in the industry also we have to time we have to take out the trumpet and clean it and fit it back. The sliver has to be condensed by forcing it to pass through the narrow space. Hence, there is an optimum size of the metal insert for every sliver linear density. So, as the sliver is made to pass through this trumpet, it experiences a lot of lateral pressure, because we are forcing the fibers to pass through a very narrow constricted space. So, while passing through this space, there is a lot of force which will be acting, reaction forces which will be acting on the sliver, and that is going to compress or condense the sliver. The insert's bore size is changed to accommodate slivers of different linear densities, and hence the bore size of those tiny trumpets which is there, it has to match the linear density of the sliver. For bulky man-made fibers, the insert could be 8 millimeter in general, which is used, that is acrylic fiber, polyester fibers, and if we use cotton fiber, viscose fibers, then the diameters are little or the bore size little less. Some indications of the sliver count and the corresponding diameter of the trumpet size is shown here, and what we see it here, that as the count of sliver becoming finer, or that is as we go this side, the count of sliver is becoming finer, and therefore, trumpet size correspondingly in terms of bore size is also reducing. That is, finer the sliver, trumpet size also has to reduce, so that we still can create lot of pressure on the fibers in order to consolidate the fibers and make a very compact sliver, which can be handled in the subsequent processes without much difficulty, that they should not easily break. The modern coiling mechanism in a modern car is little different. The cans is no longer rotated, because today's cans are very big in size. We can accommodate almost 60 kilo of sliver, 40 kilo, 60 kilo we can go. They are extremely big cans, and there was such a heavy can, if we try to rotate, then we will consume, machine will consume lot of energy, and therefore, to counter the energy consumption, the cans in the modern cars are no more rotated. Cans are actually stationary, they do not rotate. And what we do? The mechanism for spacing the coils is incorporated in the coiler head using planetary gear mechanism. The coiler plate is made to rotate in a second large plate, which itself rotates slowly. Both the plates rotate in the same directions. So, we create a situation by which the coiler plate is rotating on its own axis, and it is the plate is having a gear, and the gear is messing with another big plate which is also having internal gears, and that plate also is rotating. Both of them rotate in the same direction, and as a result what we create a situation where the coiler plate is turning on its own axis, and the axis of the coiler plate is also rotating around another axis, which we call planetary gear mechanism. It is similar to the way the earth rotates around the sun, that the earth is turning on its own axis, at the same time the earth is also rotating around the sun. A similar kind of mechanism is created, and by that the coils are laid inside the can. Such a mechanism lessens the power requirement, since the heavy cans are no longer required to be rotated. That is the advantage we get. That is how the machine has been designed. With this we stop this topic. Thank you.